think we can make it official. We're about to finish our last class before the week 4 is over. So that means we're 25% done with the semester after this class is done. Congratulations, everybody. There's a whole bunch of announcements I have on here, but first, any questions or comments, folks, to start us out? Okay, well, going down what all the scribbles are about on the Moodle page, let's just start from the top and work our way through. Here, we're on example 3 on the chapter 4 notes. But before we start the chapter 4 notes, we're going to begin taking review questions from students on whatever sections or problems you want to discuss. Exam 1 is going to be over these sections in particular. And things that can help you out on exam 1 quite a lot is your feedback on your quizzes. So if you missed hitting quiz 1 in on time, I don't have a late policy. I will still accept them for credit. And that way, once I grade that, return your feedback, we'll have a better understanding of how the work is expected to go for those questions as they relate to these sections or chapter. Similarly with quiz 2, with the quiz 2, I'm going to make every effort to grade them right away and give everyone their feedback. If you submitted a hard copy, that's perfectly fine. What I'm going to do is scan it and send it to your ISU email address so that you'll have your feedback, whether you did a hard copy or not. And I'll still hand you your actual real copy too, once you're back in class. So quiz 2, again, is really helpful to understand what the exam questions are going to look like after doing it in class, doing them in homework. And likewise, quiz number 3, it has an official due date of Thursday, September 19th. But this quiz problem is also helpful for exam number 1. If you decide to solve this early, I'll make every effort to grade it early and get it returned back to you. If you're turning it in on Monday, it might be kind of dicey since Monday is always a really busy day for me. So turning it early might mean Friday, Saturday, Sunday will be just fine. And again, if you're turning them in hard copies, that's a little bit tougher, but you're welcome to just take a cell phone screenshot of your work if you do it on a hard copy, and that would be acceptable. Just for the sake of feedback, that would just give you, again, more indications on things that you might watch out for, things you might have missed in preparation for the upcoming exam. So that's what's going on with the quizzes so far. Any questions at the moment about the announcements? Okay, then let's see, what else do I have on here? So we know that exam 1 is just going to cover this content, chapter 1 through chapter 2, those sections in particular. But other things that you definitely want to be ready to go with just for the preparation of exam 1 is this right here. I think is probably one of the more important comments I've just gotten a habit of making when I open up exams for notes. One of the things that can happen is life gets away from you. Sometimes the weekend is busier than you'd like. There's other things going on in your lives and so on. But the one thing that'll help out the most, I'd say, is put your page of notes you tend to take to the exam together before Monday. It's really, really stressful if you're putting your notes together and it's, say, like 3 o'clock on Monday with just a couple hours and a half before the exam time. That makes it so there's not as much value as there could have been, since you want your notes put together even before you're starting to study through these documents, if possible. That way you know what's all on your page of notes, you're oriented on it. It doesn't seem like a bunch of foreign information when you're sitting down on an exam. You'll be very familiar with it. Other thing to mention is don't forget your calculator, the TI-84 or your equivalent calculator if you're using a different model. I put here understanding how to use a calculator as part of the exam, but there's certain things I can help out with. I mean, if your battery dies, I might have a spare. I'll try to bring some spares to the classroom. If your calculator is just doing something weird, like maybe it's not inserting data, we've seen other weird things like maybe, let's put it over here. Maybe you don't have like L1, L2, or 3 are just gone, and now you're unable to get statistics. I can help out with those kinds of things, but knowing how to use a calculator to just get the basic summary statistics like the mean or the medians or the quartiles, that is also part of the exam. So I can't help with those kinds of questions. Because of that, I'm saying good additional comment to put here is if you're worried about maybe forgetting a step on the calculator when you're going to do the exam, no harm in using the notes that you're allowed to bring to class and just write out the steps to do the basic things that we've done. Pretty much the only thing that we really need on the calculator that requires steps is the whole process of, let me get out of here, hitting the stat key, hitting enter here to input your data, hitting the stat key again, going over to calculate, hitting enter a bunch of times to find your data, and knowing you have to use down arrow to get the other data there. So that's really just the major thing we're going to be really using on exam 1, grabbing those summary statistics. We'll be building more on that as we go along, but so exam one doesn't use a calculator in a major way, but it's good to have that written down in your notes if you feel like it's still a little bit vague. You don't want to lose your way on a timed exam. Well, that's my big spiel for getting ready for our upcoming exam next week. Any last questions or comments, folks, about the exam itself? Okay, it's a 70-minute timed exam in this classroom, but my goal is always for this kind of class to write about a 50 to 60-minute exam on average. So the typical student, say the central 50% of times are somewhere inside there, probably more than the central 50%. That way there's going to be extra time at the end to double check your work and that kind of stuff. So don't feel like you have to race through it. And if it feels like you solved your exam in 20 minutes and you just want to get out of here, you're welcome to do so. But I encourage you to go slow, pace yourself, watch the clock, that kind of stuff. I'll probably have the clock just up here so that you don't have to bring your neck over to see it. And you'll be in great shape. So that's my spiel for getting prepared for the exam. Now at this stage of the class today, I'll turn it over to you folks. What questions would you like to take a look at or discuss about reviewing the exam one? Anyone have any problems that they'd like to take another look at?
It's not necessarily a problem, but on the calculator,
Yeah,
when you get your calculations answered, can we go over what each of those means? Like I know that the MED is the median and the Q1 is obviously Q1,
yeah,
but which one is standard deviation, which one's mean? Can you just go over that one again?
absolutely. Let me open a new document here. I'll call this exam one review questions. Let me get this thing fit first. There we go. And after we are done with their exam one review questions, if we run out of questions, I'll post the results right above here. I'll just say, well, exam one review questions. So the things that we did in class. So what we need is some data to take a look at that. Sorry, let me move my windows around. It's always a little tricky to get just right sometimes. There we go. So maybe to kind of start off with that question, let's do a problem from one of these documents where we actually have data. So we'll throw in some actual data to the calculator, refresh that whole process, and then look at all the summary statistics. So I don't know if anyone has a preferred version, but these are new problems. So let's take a look at this one first. I just want something with a quantitative variable. That's kind of a lot of information. I'll go with maybe, that ought to do it. This one looks like hypnotherapy. We're looking specifically at the data, so I'm just going to look at this part right here rather than the part A and B. But if you would like to see those parts solved, then let me know and I'll be happy to jump back to it. Okay, so imagine this is a real exam one question. We want to get summary statistics. Here's what the process will look like. So grab the calculator you're most familiar with. I think for most people, it would be the TI-84. That's the one we're teaching. But if you're familiar with another calculator that you prefer to use, you're welcome to do so. Only thing that's a little sketchy about that is I probably don't know how to use your other calculator, especially if it's a Casio. So you'll have to be really ready to go with a different model. Well, to get out of this screen, you can just hit clear. Now to get the data imported, our mantra is hit the stat key, enter right away. We'll probably have data inside there, so go up arrow. Hit the clear button with L1 is highlighted in this way, and enter. So now we can start importing all the data. And going row-wise, we've got 8.2, 9.1, 7.7, 8.6, 6.9, 11.2. It's good to be accurate even on an exam, but if you did make a small mistake on one of the numbers, your numbers might be just a little bit off. You're not going to lose the whole question. I would be able to tell, unlike my stats lab will complain, I'll be able to tell that maybe you just had a number that was a little bit weird here. But watch out if you accidentally put in instead of 11.2, 112, that will throw it completely off. And if it's something like that, I wouldn't have any idea what happened to the numbers. So watch out for the decimal points most of all, I guess is the takeaway there. Then 10.1, 9.9, 8.9, 9.2, 7.5, and 10.5. So that's 12 pieces of data. We can tell because it says L113, so we didn't miss anybody. Next thing we'll hit is the stat button right on this screen. We don't have to change anything. With the data imported, we can now go to the calculate tab or just calc. So that should be highlighted. And this is the portion where I usually just say hit enter a bunch of times and you'll be all set. And here's our output. So let's take a couple screenshots of this. Your output comes in as two different screens. First, we have screen one, some of the more typical statistics if you have some symmetry in your data. Your data is, oh, what did I do? I think I clicked on the wrong thing. If your data is less symmetric, you're probably looking at these data. Geez, where did I go? There it is. So that's pretty much all of the output, and all in one shot. So now dissecting all this here. Some of the information is not super helpful for us. Other things are like an internal check, because they told us there was 12 subjects. You should see a 12 right here. If it says 13, then something went wrong with the data or otherwise. But let's start on this screen right here. Most textbooks, well, I shouldn't say most, maybe about half in the country, use X bar for their sample mean of the data. Our book uses Y bar. So we have Y bar equals 8 point, or maybe it's a little bit easier to do it this way. That's our quantity for Y bar, which is the sample mean. Sorry, that didn't quite take right there. Let me try it this way. So the sample mean goes there. Then there's other interesting informations. This is the sum of all the observations, sum of all the observations squared, but we don't have any real business with those outputs. What we need next is this one, SX. So S is the sample standard deviation, and it's this quantity right here. Honestly, I would say screen one, when you do this output, is kind of the trickiest one because you have to filter out a whole bunch of stuff. We're not using that, nor that, nor that. And the N is 12. I mean, that's good, but we didn't need it. You only need the first result and the one that goes SX. So that takes care of that screen there. Moving on to another one. This one, again, is not too bad. We have everything we need. The minimum, quartile 1, median, and quartile 3. Maybe the one thing we might write is M, which is the median, is equal to the 50th percentile, which is this quantity right here. So we're given the 50th percentile right away. We're also given quartile 1, 25th percentile, quartile 3, the 75th percentile. But one thing the calculator doesn't give to us is this, interquartile range. Anyone recall how to calculate that value? Exactly. So we have to go to these values that are listed. We would look here, and just as you said, Q3 minus Q1. Whatever those outputs happen to be in the problem. In this problem, it'd be 10 minus 7.95. So those are the major outputs we would use in the calculator. Again, everything here is pretty good, except I don't feel like I want to necessarily scratch it out, but it's more of a distraction sometimes. I'll leave them all scratched out here just to signify these are the things we'd be using. Any questions at all, folks, so far? Okay, by the way, now that we have this, notice we have two kinds of statistics. The sample mean describes the center. The sample standard deviation, S, this describes the spread, or you could say variability. Let's say both. Spread, variability. Both are mentioning the same thing, so that's considered synonymous. I usually say variability, but our book kind of goes back and forth. I think they most often say spread. So over here, same kind of idea. The median M, this describes the center. This is how spread out the central 50% is. So this describes the spread or variability. So this kind of implies already an important question. When do you use which statistics? For example, you might have data that is highly skewed. If your data is highly skewed, you probably are looking at something like this for the histogram. Make it have an outlier just because the bar went that far. So if your data is highly skewed, use for the center, and we recall what value we must use. Been a while since we looked at that question, so this is a true review question in a real sense. If we had skewed data, say that's your histogram, what would you use to describe the center of the data where everybody's accumulating? It would be the median. Good call. Just because this is skewed right or skewed left, for the center, use the median.
That's for both skewed?
Exactly. Skewed left or skewed right. Absolutely. So we know if we have really skewed data, you'd be using this value, the median of 9. And for the spread or variability, I'll just call it spread. The moment you make a choice, median, you just pick interquartile range. So in a real sense, these statistics are paired up. The sample mean goes with the sample standard deviation. In fact, you can't even calculate the sample standard deviation without the sample mean. And over here, median goes with interquartile range. So IQR. The reason I kind of tapping the brakes on this review question right here and asking this additional question is sometimes this could be the most trickiest exam 1 question. You might be faced with data, something like this, and a question could simply ask, which statistic would you use to describe the center? I'm not asking you to calculate anything. I'm just asking you name the statistic, either the median or the sample mean. Again, that's a pretty confusing question if it's out of nowhere. But I think we did some of them on the sample exams. Let me see. For example, this one, nope, not quite, but this would be one of the cases we would use the median in the interquartile range. So the dual to that, let's finish it off, is for at least roughly symmetric data, for the center, once I spell that right, center, there we go, T goes before the E there. And for the spread, really, this one's not so bad because in a certain sense, these are the default statistics that we would like to use as often as we're allowed to. That's why it's phrased this way, at least roughly symmetric, meaning we're allowing a lot of deviations from perfect symmetry and still using the statistics. So for at least some roughly symmetric data, the shape could be this. I want to make this one almost borderline where there's a clear skew, but we would still use the sample mean and the sample standard deviation. It might look about like this. So, well, maybe, let's leave it like that. It looks like it has a skew to the left because of the data that's right here, but we would consider this to be roughly symmetric. For the center, use Y bar, and for the spread, use S. So these go together with data that looks like it has some degree of symmetry to it, or perfect symmetry. But once the data looks bad, once it's skewed so badly, there's no inkling of symmetry on it, we have to use those other 2 statistics. Well, that's the big spiel on choosing statistics. Again, that's a pretty tricky exam question. Just to reiterate, if you see a question that says, which statistic best describes the center, or which statistic best describes the spread, you're not calculating anything, you're just doing this. Either say median, or say Y bar S, or median IQR rather. Well, any last questions, folks, with these concepts here? Okay, I'll turn it back over to the class again. Any other questions folks would like to take a look at? Including anyone in Zoom as well. You could use chat as well if you prefer. Sometimes that's the best question is, what are the questions? But let's give it some time. If we don't have any questions, that's okay too. In chapter 4, we'll do a bunch of stuff that does hit on exam 1 material. But let's give it a minute to see if anyone has a question while you're looking through.
We're gonna be using the equation for one is equal to one over n, and then it's the sigma, I think it's called, and then on n on top, I is equal to one, then y, one. We're gonna be using that on the exam.
No, we're pretty much for any question that needs some statistics, we're going to be using this right here. And there was another kind of problem that we did that I think it was kind of confusing why we did it. Let me turn to that one really quick. I think it was in spread. I have asked this one as an exam question in the past, but I'm not going to ask this one again on our exam. Really, the major reason to do this problem was we were just investigating what is going on with the formulas up here. How do they work? So it was like a quick demonstration of the format of the formulas, the way it all comes together. But at the end of the day, on an attempt and a timed exam, if you had data like this and you needed the sample mean, the variance, or the standard deviation, then you would be asked to use your calculator to run through it. It would just take too much time, even for 4 to 5 pieces of data, to actually fit that into an exam. But now that I mentioned that, there's another possible exam 1 question that could come up. I'm not totally sure if I asked this, but just in case, let's cover all bases. So we had some output here. Let me see if I can bring it back up. So consider output where you have standard deviation S. I'm looking at this where it says SX, and it came out as 1.29. Oh, let's say we rounded to 4 decimal places, 1.2904. A question that could come up, again, I'm not sure if I asked this one, so I'm just kind of covering all bases because this one would be tricky. It could be, what is the variance? The variance was an important formula because you actually need to calculate the variance in order to get the standard deviation. So let's take a look at the formulas now that we had that page open. So here are the relevant formulas. Imagine maybe this is on your page of notes. It wouldn't be because you're going to directly use a formula, but it could be because of formulas like this right here. So if you know the standard deviation, that means right here, the value is known. The variance is equal to S squared. So what are we doing? If we're squaring S, we're squaring this quantity right here, which is squaring this quantity, giving us back the variance. So in the end of the day, if you know standard deviation, you take the quantity 1.2904, and just raise it to the power of 2, and that's going to give you your variance back. So variance is always indicated with S squared, and now in the calculator, let's go 1.2904. Easiest way to square something, because it's done all the time, is this button right here. It's kind of in the middle on the very left column. It's right where you see that square root symbol as well. So that gives us 1.6651. And that's our variance. Kind of debating whether I want to leave that on there. Let me put it over here maybe. Any questions about that, folks? Recovering the variance when you have a known standard deviation? Okay, well, those are good questions. It's pretty much questions about what we'll do with formulas like these are a really great question in this class, since you'll notice we almost never work directly with that formula. we did it just one time really right over here. Again, part of the reason was sometimes in a statistics class, a calculator like this just seems like a black mystery box where numbers go in, answers come out. Hard to know what even really happened in the calculator. And this was just an attempt to try to explain what is the calculator doing, how the formulas are working. So I'd say the worst question along those lines where formulas like this could come into play would be this one right here. That would be a pretty tricky question. Other questions at the moment, folks? Okay, let's save this up. That'll conclude our review questions for the day for exam one. I think we've spent some good time looking at different questions. For other exams, we'll do the same kind of thing. If people have a lot of questions, I'll just assume that that's time well spent. But for the moment, we're going to turn over to section or chapter 4, finish off the notes there. And in section 5.1, which will likely start today, depending on where we end up, this one's not so bad either in the sense of really example 1 is an exam 1 review question in the sense that we're dealing with these kinds of statistics. And example 2, we'll calculate some more statistics. So all that's still relative to exam 1 kind of material. So let's take a look at where we left off. Oh, let me save this first so I don't forget. And these notes that we were just working on, I'm going to put them right over here on top of the 2 exam review problems. Okay, so here's where we left off on Wednesday's class. I think we had like 5 minutes, so we just talked through the problem. We didn't do too much with it. This problem is about lung strength, and FEV is just a measure of how much air you can blow out in 1 second after taking a full inspiration of air. So we have a data file for this one. Let's take a look at it once more. It's the file that goes FEV, and it's kind of hard to look at. Let me see if I can zoom in on it. Oh, everything sort of zooms out. It's okay, I guess. So here's the file. And here on the left column is the age of the children. This is the major variable that we're investigating. But every other variable that they recorded is still relevant to this. Scrolling through, if we look at, say, just one row, this person, this individual was 9 years old. This was their FEV value, so 3.681 liters. This was the height, I think, in centimeters. 1 indicates male and 0 indicates non-smoking. So these are the kind of individuals we're looking at on this whole data set. And by the way, it's a ginormous one. I think it has a few hundred observations inside here. If you take just this variable, FEV, put it in a histogram, that's not too unusual based on what we've been doing, then this is the result that you'd get once I find out where my stuff is. Let me fix my windows. This Firefox browser has hidden all my things on the bottom. There we go. So here's FEV, where everything is just poured into one spot. If you saw that, well, we can make some conclusions here. We could say that, well, the typical value for lung strength for all of the children in this data set seems to be right around here, maybe about 2.5. Also, this would be considered symmetric, but it does have some skew to it. What direction would you say it's skewed towards? Yeah, absolutely. It's kind of trailing off this way a little bit more than to the left. So if we were to explain what the shape is of this data, we'd say this is unimodal. Mostly symmetric. And an answer of symmetric, mostly symmetric, is completely fine on this. But if you want just to add a little bit more detail, you could say with a slight right skew. And I think we kind of agreed last time, this is debatable, but for me, if I was to put a curve to this data, the curve would look like this. Shoots up really high, peaks around here because there's one clear peak to that. That's why we're calling it unimodal. Then it dives down, but a little bit more gently in this kind of shape. So this is the shape I would expect for slight right skew. It means all the data I see here is about what I should see for a slight right skew. Nothing seems too unusual. In other words, there are no apparent outliers, at least to my eye. If some people said that it looks like these could potentially be outliers right here, I would agree with you. We would have to double check by using a 1.5 IQR rule of thumb, that kind of thing, to really know for sure. But just based on the graphics, that's pretty debatable. I would edge towards the conclusion of no outliers if I saw that graph. So that's FEV variable all in one shot. So this stuff, let me try to fix this window so we can call it back a little bit easier. But if we try to pull in other data, say the age data as well, now we have a display that goes this way. Here we saw a lot of interesting things when we were taking a look at this. First of all, these are all box plots. So let's recall what we mean when we say a box plot. Say, take a look at just one of them, maybe the 4-year-olds, because this is a filled out box plot. Something like this one where it's a little bit degenerate. There's no whiskers going up and down. It could mean several things. Maybe the minimum is quartile 1, the maximum is quartile 3, but more likely, maybe there's just 3 observations for the 3-year-olds in this situation. So 3 data values was plotted in that way. But let's focus on the 4-year-olds. We looked at that. What would you say this value right here corresponds to? Absolutely. It'd be about 1.4 in terms of FEV, but what quantity or statistic would that be? Sorry, say again? Good call. That one would be the median. So the heavy line in the box plot is referring to the median. M is 1.4 for the 4-year-olds. Likewise, for looking at this line right here, going that way, maybe about a 1.5. And that would be quartile 1 for the 4-year-olds and so on. Going this way, that one's kind of hard to say. Maybe, let's just say about 1.01, or I'll just say 1. Maybe my arrow just kind of went off. It looks like it actually is slightly higher than 1. I'm going to round it to 1 just for ease. So that 1 there is equal to, oh, hang on. I said quartile 1. I'm going to say quartile 1 again. Looks like there's a mistake on here. Which one would you say is correct, the top or the bottom? Right, sorry for that mistake right there. The higher one is quartile 3. So that should have been Q3. Then this whisker gives us a value going this way. Kind of hard to estimate that value. Maybe it's about a 1.7 or so, but that would be the max. And this would be maybe at about 0.8. That would be the minimum. So that's what the box plot is saying. Whenever we see all this, we'll only do it for the 1 count or the 1 category, 4-year-olds. Otherwise, this would get a little too busy. But now that we took our data set, which looked like this, we took age, which is considered to be a quantitative variable, but look at how it's being used. It's actually categorizing everybody's FEV values according to the actual age. So this is something that doesn't get talked a lot about in a statistics class with variables. The designation of whether something is truly quantitative or truly categorical purely depends on how the statistician, the people analyzing the data, actually uses the variable. If all they ever do with age is categorize the children in this way, it's categorical now. If they did a little bit more and treat it quantitative, then it becomes more complicated. But from what we can see, the age variable is being treated as categorical, and it's just categories of FEV values depending on age. So part A is an interesting question. Let's take this screenshot here. We're being asked, what does the side-by-side box plots, so these ones going that way, say about the FEV distribution, those lung strength values? I'll put that down there just for a real quick reference, that cannot be discerned from a histogram. Let's see if I could try to get that histogram a little higher. There it goes.
15-year-olds have more range.
Yeah, that's a really good point. There's a huge variability. The range goes from the minimum to the maximum, and even interquartile range is pretty large on this one. Look at how stable these are, but when you're a developing human, everyone's pretty similar at age 5. By the time you're 15, it's going to depend on, did you do sports? Do you have a medical condition? Variability becomes more extreme on the higher end of ages. So let's add that there. The range for the 15-year-olds is larger than for any other category. And that's kind of the sad thing about the FEV histogram. When it just plotted the FEV values, it ignored all of the other variables. And so all the information here just got glommed into one display. I can't say anything about 15-year-olds, 14-year-olds, and so on. We're talking about the total data set as one big summary in the histogram. But the categorical variable splitting off into age like this is painting a whole different picture. So now we suddenly see what's happening to each of the age groups, like you were mentioning. Any other patterns folks would want to mention?
The medians kind of line up in an angle, whereas the ranges kind of go up and down.
Yeah, so the median is pretty important. The median is always going to be the center of the data. If we plot a line that goes like this, let's try to make a line hit all of the median values as a gentle, smooth curve. It may not hit them perfectly, especially out in this area. If I try to get it roughly close to each of them, it kind of goes like that. That tells us as the age increases, FEV, which is the lung strength, also increases. Kind of a gradual increase. Maybe it's a little bit faster at first. Right around here, it looks like it's a little bit more gradual, but the variability becoming larger is kind of muddying the waters. But let's mention that as well. There's no way you can tell that at all here, that there's a pattern on ages and the FEV variable whatsoever, looking at the histogram. So here we can say, we can see that the medians gradually increase as, that's 2 letters for as, there we go, age increases. Again, that's something you can never detect just by the histogram down below here. Let's try for one last thing. Anyone see one other thing you could never find here that is visible on the actual box plot? Maybe one review question that we did hit on the box plot was, what are these? Yeah, good call. There's a bunch of outliers all of a sudden, but we looked at our histogram here and maybe there's a couple, but that was debatable. I would have still stuck with the answer. There's no apparent outliers based on that graphic. But if you separate by age and look at these values, that's the 1.5 IQR rule of thumb in play. There's a whole bunch of them now suddenly available. And only for certain ages, that's interesting. Somehow 6-year-old had 2 outliers. Then around 10, 11, 12, there's a whole bunch, a good cluster around here. Again, the fact that there's outliers alone is not something you can see on the histogram. So let's add that here. We now see outliers for certain ages but in the histogram, none are apparent. So what is an outlier really? An outlier is just an observation that doesn't fit the usual pattern. But when we say the usual pattern, that is a huge catch-all statement. What we're meaning is, it depends on how you plot the data. A plot like this, ignoring other variables, hides the outliers. But this is one of the reasons we really like box plots. We're comparing against a lot of distributions, all the ages, and suddenly a story is emerging. Outliers appear in a different graphic. If we plot these in some different way, there's a lots of different ways to visualize these data. What about by height, for example? Height affects lung strength. Taller people are more massive, and so their lungs should be. We ignored that entirely on this plot as well. So there's a huge story you can paint about these data. There's probably many different kinds of esoteric outliers you could find by visualizing it in different ways. But our goal here was just to get a feel for what is a box plot and how is it used to compare different categories. This is one of those kinds of cases where it really shines.
Is there a question that will ask us which plot we should use, like a histogram or a box plot?
I don't think I asked a direct question like that, but I did ask questions along the lines of, if I give you some data, should you use a histogram or should you use a bar chart?
Yeah.
So that would be more about, is it quantitative or is it categorical? So I'd be mostly asking those kinds of questions. Other questions at the moment? Okay, so again, like we mentioned, there are loads of different ways to visualize these data. For example, the smoking variable, we're completely ignoring it, right? That's probably the most important variable if we're talking about lung strength. So why is it ignored? Well, let's see if we have it down here somewhere. We do. So if we do a box plot for the FEV values, and all we're concerned about is how it relates to smoking values. Recall 0 means non-smokers, 1 means the smokers. Here's what it looks like. Instructions on this one say, comment on the display using the context. And there's a lot of wild things you could say about this, but let's take it all in. So horizontally is lung strength. For non-smokers, this is the median at about 2 point, that's kind of hard to say. Let's put down a number, maybe about 2.5. If we look at the smoking group, the median for this one is maybe 3.1, 3.2. About here, maybe. I'll call it a 3.2 maybe. This display looks kind of unusual, would you say? It's essentially saying, if you look at the non-smokers, then 50% of all non-smokers have an FEV value that goes from here to here. If you look at the children that were smokers, 50% of them have FEV values that go from here to here. It's higher. It's significantly higher, but not for all observations, because here's some outliers. The non-smokers here mostly beat out all of the smokers except for these two. Looks like they lost to a few of the smokers in this category, but the rest of them have higher lung strength. But by and large, we're more interested in the central 50% because that captures the typical experience. Looks like non-smokers have weaker lung strength in this data set than the actual smokers. It starts to make it sound like the data set is a lie. So let's say that right away. We have that the lung strength, that's the FEV, forced expiratory volume or something. We have the lung strength is stronger for the children that smoke. Again, not that they literally smoke in all cases, but they're probably exposed to secondhand smoke regularly in their home life. So what would you say is an explanation for that? Is the data just wrong, or is something else happening? Sorry, say again. Possibly, but I would say with the way that they're measuring this, if you were coughing a lot, you might actually get a lower score on the test for lung strength. I'm not completely sure. I've never actually taken that test or administered it or anything like that. But I think there's probably more going on about that. Let's take a look at the variables.
I think that this graph doesn't necessarily show how much data was actually taken, because we're kind of left to assume that the amount of people that are number one in the smokers category is an equal amount to the people in non-smokers. But when you actually look at the data, there's way more non-smokers.
Right. That's one thing you can't see in the box plot. And that's a good comment. Let me put it here. The box plot does not show numbers of, oh, and I didn't think this through. Let me get some more space. We'll just redo the. The box plot does not show the numbers of individuals in each category. And I'm glad you mentioned that because we're thinking about the data a little bit more carefully now. If we're wondering about what is going on with the 0 versus the ones, well, let's just take a look. Watch the ages on the left as we scroll through. Lots of zeros to start, non-smokers. The ages are young. Let's zoom in maybe a little bit more. So we're scrolling, and well, still mostly just zeros. Now the ones are showing up, but the ages are older now. Let's see, 14 again on that one, a 13 on that one, 11 and a 14 on that one. I think if you look really hard, there's a 6-year-old that smokes, but that one was actually atypical. In a certain way, that's considered an outlier. That didn't fit the normal pattern for smoking versus not smoking. So there seems to be an age component here, right? Sure, there's not a lot of smoking children. That's a good thing. There's mostly non-smoking children. But by and large, it seems that if a children is smoking, they're probably older. Would you agree with that just by thinking about the data or just the context of the data? Well, if the children are older, would you agree that their lung strength is just better because they're bigger children, that they can fit more air in their lungs in the first place? That's what's going on with these data. And that's the danger of a data analysis. When you have variables like these, they are absolutely interconnected variables. And if you take a picture of FEV, smoking versus non-smoking, it looks like a total lie, but that's the right picture because there's another variable tying it all together. We can say, this is explained by, this is possibly explained by, I haven't completed an analysis of this data. So let's say, this is possibly explained by the fact, or let's say I don't want to say fact, we'd have to check that. This is possibly explained by older children being more likely to smoke. And I want to say here, and the fact that older children simply have larger lungs. But again, I don't like this problem a lot because data is really weird. When you pull a data with multiple variables like we just did, you can paint some crazy looking pictures that makes you feel like nothing's right about the data until you start thinking about how all the variables are interacting potentially. Well, any last questions, folks, with taking a look at those graphics? Any additions you'd like to put in? Okay, like before, we might have said something about outliers. There was only outliers on this display for the non-smoking children. So that's pretty interesting as well. But I would say this display was more about the fact that it just looked wrong in the first place. So I think this would be a good place to end on when it says, comment on this display using the context. So again, I'd say chapter 4, it was all about comparing distributions, and that's what we're doing. This is the FEV distribution compared against another FEV distribution, but across a categorical variable, smoking versus non-smoking. When you go to do these problems in the homework, you'll see a lot of stuff kind of like this. Sometimes it's multiple histograms, sometimes multiple box plots. But all we're doing is comparing groups and making these sort of comments. So let's save that up. We did it, folks. That's the conclusion of chapter 4. It's a pretty small section in the homework, so it's not going to be hugely represented on exam 2, probably just a single question. Well, after that's done, next thing we can go into is chapter 5. Chapter 5 is a big chapter. We're going to look into z-scores, standardizing data, the normal model, which is great because in our calculator, one of the reasons we needed the TID for is we're going to start using this setup. We'll start hitting second, the vars key right here, to pull up things like normal CDF or inverse norm. We'll be using those functions a lot with the normal distribution in chapter 5. But to get a feel for how all that goes, we have to talk a lot more about standard deviation. So that's probably because a dialog box is open. Please close the box. After I close that box, apparently, there we go. So here we'll take another look at standard deviation. I don't want to go too far in this section since I notice we got about 19 more minutes and some change. So it looks like we might end on just example 1. We'll see where we end up. So the major component of this section is something called a z-score. And z-scores are great. There's a lot of great values to using a z-score. We'll see different questions that you couldn't really answer without them. The way it goes is your z-score takes a data value. From that data value, you subtract the mean, and then you divide by the standard deviation. So y always denotes observation in the data. That's the sample mean, sample standard deviation. What does the z-score do? Well, it has units, and the units is number of standard deviations. It tells you how many standard deviations that your data value y is going to be away from the sample mean. The z-score can be either positive or negative. It'll be positive when the data value, that's y, is going to be larger than your mean, and negative when the data value, y, is smaller than the mean. So the z-score just tells you how many standard deviations is a typical observation away from the center measured by sample mean. So here's a fun example to get along those lines. I pulled these data from my computer using a Windows 10 machine. They have a weather app on there. And I gave a historical weather counts, as well as the temperature on the 11th when I took a look at it, and a forecast all the way to the 30th. That's probably not reliable. So today it got really cold. Tomorrow it's predicted to be a little bit warmer. But what I did was I took the highs. I took all the highs, 91 degrees, 90 degrees, 82 degrees, all the way to the 30th, 68 degrees, put it in a calculator like this one. I produced those two statistics. I didn't ask us to do it because that's really honestly kind of tedious. I try to keep them smaller for typing in stuff into the calculator. So the sample mean for all these observations, the month of September, is 76 degrees Fahrenheit. Kind of nice, balmy. Standard deviation, because this is Idaho, is huge, 11.1 degrees. If we lived closer to like an ocean community, variability shrinks on temperature a lot. This might be like 3 degrees Fahrenheit in standard deviation. Any questions, folks, about what's going on with the data or the statistics? Okay. It says calculate the z-score, so let's take this as just a screenshot to help us along the way. We just looked at that formula. Don't expect us to memorize it that quickly. Part A says, calculate the z-score for the temperature high on September 1st. Oh, I need to go up and actually look that up. The high on September 1st was 91 degrees, so that was kind of a nice day. What day was that? Oh, it was also a weekend. Cool. So we want the z-score for temperature on September 1st. What that is asking is, we want to know that's pretty far away from the center. How many standard deviations away is it? If it's something like 3 standard deviations away, it's tremendously unusual. If it's like 0.5 standard deviations away, that's pretty typical. The way we calculate it is through this thing. The z-score is designated by the letter z, makes sense, that's why we call it a z-score. You take the data value, called y, subtract the sample mean, y bar, and divide by the standard deviation s. Using the z-score is not too terrible as far as the y bar symbol goes, the s symbol goes. You're just plugging those in, so that's kind of nice. I would say the most confusing thing about using the z-score is where they say this. Oh, I want to change my color. Let me use this. Where they say data value, sometimes I think that's the foggiest thing about the z-score. This problem said, calculate the z-score for the temperature high on September 1st. They're referring to the data value when they say that. And that would be this data value here, just the 91 because we're focusing on the highs of the data. So it goes with 91 to start. I'll drop the units and just put in the 91 and put in the unit once we calculate our answer. Subtract. Sample mean 76 degrees. And then divide by standard deviation, 11.1 degrees. So that's how the z-score computation always goes. No matter what, keep in mind that the sample mean in your numerator always comes last after the negative sign. So if you keep that down pat, then you're always in great shape. So let's put this in the calculator. If you have a weird screen here that you don't want to deal with, you can either hit clear. If that doesn't do it, second, and the quit button often just takes you right out of whatever window you're in. I'll do this one in stages. If you go top and the bottom, it would be 91 minus 76. Then just hit enter right away to get a value. Then divide that value by hitting the division key, 11.1. So we have 1.35 standard deviations, as they said, to one decimal place. Let's round it to 1.4. So the original data had units of degrees Fahrenheit. Numerator's degrees Fahrenheit here, and I guess I put it on that one spot, but not everywhere else. But because we're also dividing by degrees Fahrenheit, as a unit degrees is just gone from the z-score. All that's left over is standard deviations. So the 91 degrees, it felt unusually warm, but you know, it's not too unusual. I would say that's pretty typical. Once we get to 2 standard deviations and beyond, it becomes less and less normal. 3 standard deviations and beyond starts to look like an outlier at that situation. Well, any questions at all, folks, on calculating that z-score? Okay, somehow, some way, we're going to take z-scores, use them to define something called the standard normal curve. And so it's a little interesting side topic on the way to what we're describing earlier on that calculator. So with that z-score down, again, its whole purpose is to get a feel for what's typical, what's atypical. I tried to pick the highest temperature I saw on here, but it really wasn't that remarkable. Let's put a quick note though. A z-score above 2 or below -2 shows observations that are less typical. And the other related comment was a z-score above 3 or below -3 shows highly, like mangled highly. Let me try to spell that again. Highly unusual observations. So if someone tells you that they can do some task and their z-score on that is 3 standard deviations or 3.2 standard deviations, they're basically saying that they're practically a genius at that task, whatever it happened to be. If you're at 1.4 standard deviations, sure, it's a little bit unusual, but it's still pretty typical within the sample mean and the standard deviation of that data. Any questions at all, folks, with understanding z-scores, so those standard deviations? Okay, let's try this out again. Part B now says, same problem, so we're talking about those temperature values. Suppose that the temperature high on September 13th, so that's tomorrow, turns out to have a z-score of negative 1.73. What was the temperature on that day? So this is like the reverse question. On the question above, we just grabbed the temperature on September 1st, 91 degrees, plugged it into the formula, and cranked out 1.4 standard deviations. But on this problem, it starts with a z-score, and we're wondering, what was the temperature on that day? Kind of an unusual problem, but think of this one as just another way to get more familiar with what the formula is trying to say. The way I would always start this one is just write down the formula. Z equals y minus y bar, all of which is divided by S. So when they said we have a z-score, that's what's going over here on the far left of the equation. In place of z, we're putting in negative 1.73. They're asking, what was the temperature on that day? And that's this, y, the data value. That's the one thing that we don't have information on. So we just leave it right where it is and plug in our summary statistics. Yeah, absolutely. An X right here would be just fine. And honestly, that's how we've been doing it for a number of years until we went back to this book. So I'm still adjusting personally on that. So whether Y or X, you're going to be in great shape. Next thing, we just plug in the other statistics. 76 degrees for Y bar, 11.1 degrees for Fahrenheit. And now our whole task is to solve for Y. I want to mention we don't do a lot of equation solving in this class, but this is pretty much the one and only time we really do have to solve an equation. We'll do this twice just to get some extra practice on it. So if I was to solve this equation, I wouldn't divide 11.1 into the y and the negative 76, although you can if you want to. I think it's just a little bit cleaner and easier to multiply both sides by 11.1, eliminating that denominator. So this next step would be, let me write it down here so we have a clean starting spot before we start doing those steps. Negative 1.73 is equal to y minus 76 over 11.1. So on the left, I'm going to multiply by 11.1. On the right, I'll put parentheses around it so I can indicate multiplication by 11.1. Or on both, why not? Can't hurt. In the calculator, though, this is what I'd be doing. 11.1 times, oh, this gets a little tricky. We need a negative sign in here, and that's the symbol down below, that negative sign. 1.73. Honestly, that makes me uncomfortable. I would usually put parentheses around this. Let me see if it even works. I would almost never type it that way. It works, that's kind of nice. Usually I would do it this way out of paranoia and safety. 11.1 times with a parenthesis, negative 1.73. Same value though. So we get, go to paper. On the far left, it's negative, oh, we got it. Oh geez, what did I do? It's negative 19.203 equals, on the right-hand side, we cancel the denominator, so just y minus 76. Exactly. What I would do is, in the calculator, just go plus 76, and we're home free. We're rounding to one decimal place, so we'll say 56.8 altogether. So 56.8 degrees equals y. So if we're at negative 1.73, that means this observation is 1.73 standard deviations. It has a negative sign, so we'll say below the mean. That seems right. I mean, it's definitely below the mean. The mean was 76 degrees. This is 56.8 degrees. And I would say it's starting to become a slightly unusual observation if that really happens tomorrow. But oh, on the right up here. Well, if I went with the negative here, this is what's really weird in the writing. It would cause a double negative because I said below. The below itself kind of conveys the negative. It's really weird, but if you did go with that, sorry, say again.
From the mean, not below the mean.
Yes, absolutely. So from like that makes it absolutely correct. And that's just a different stylistic way to say the same thing. So yeah, this would be a great way to say it. Other questions so far, folks? Okay, so that's standard deviation so far with as they relate to z-scores. We'll be doing a little bit more with this kind of stuff after we come back from our first exam. I think this is probably a good stopping point for us. Our next problem will take not too long to go through, but we don't want to rush through any of these. By the way, one fun thing to use with z-scores is you can answer a question like this one. This is pretty much how the chapter section 5.1 starts, this kind of problem. It says a student took two national aptitude tests. The mean and standard deviation were 475, 100 for the first test. So they have statistics on that one. Second test mean was 30 and second test standard deviation was 8. The student scored 625 points on the first test, 45 points on the second test. But now the question is, on which test did the student actually do better on? That's kind of hard to say, right? 625 on the first test. Well, the first test mean was 425. It looks like that's really great. 45 on the second test, but the mean of the second test was 30. That's really great too. It's almost impossible to answer this question unless you're involving the standard deviation as well. So that's why we need z-scores. The mean is never the full story. We also have to say, how spread out is the data? What is its variability? But only this, just as it is, and we'll come back to it on Wednesday's class next week. Any last questions at all, folks, before we call it a day? Okay, well, have a great weekend, folks. If you have any questions whatsoever when you're starting this weekend, don't hesitate to email me. I'll be happy to help out. It's going to be next Monday, yeah. Thank you.
Sorry, I was late. There was a stupid train.
I hear ya. That train has made me be late for teaching, so
It's really
yeah,
frustrating.
it's the worst.
I went all the way around. Yeah. And so, cause I didn't realize, I never get stopped at the train.
Yeah.
Oh, my friend. I went all the
Yeah,
way
it's the
around.
worst.
Ended up going down that train.
It's gonna be in this room here, yeah.
Yeah.
Yeah, I started driving under the tunnel, just taking an extra mile to work because it's worth not having your whole day upended like that.
But there was like 50 cars and they're all like, no, you're turning around, peace out.
Yeah, I pulled it,
Yeah.
I pulled a line going down.
Jeez.
I felt bad, cause like, dude, I gave one to the whole thing. No. Exactly, one piece. Yeah, that's fine. I have one at home and I still have my computer out there. So I mean, yeah. Eat
Thank you,
it.
sir.
Oh, it's gonna be like a Scantron type test, or is it just?
It'll be a paper test. I'll have it all printed out and you'll just write your answers, kind of like these documents here. And pretty similar to the quizzes as well.
Every time I come in, I'm like, I'm one student, but I take up 6 chairs. Dude, I take up 2 and I already
That's
feel like.
easier.
that.
I can spread myself out.
I don't know how you sit up there. I'm like, oh,
Really, I guess I do do one of it, mostly because I like hear the teachers talk, I need to see their mouths. for some
Yeah,
reason.
no, I.
So,
I don't
yeah.
pay attention, I don't.
Yeah, so that's my only reasoning for sitting.
Oh, sometimes people say a good sentence, you're like, well, that's a good one, you get like halfway through, you're like, I don't know the rest of the sentence, but I can't, you repeat it, you said it, you said. She said the whole
I
thing.
know.
That's why I like this important thing.
Yeah,
I don't do that only because that's nice about his class, though, he reports it. Do you repost it? Yeah, he posted on YouTube, oh,
Yeah, so you can find them
so you can like follow along again, you clear all your notes.
right here under the Zoom link.
Okay,
Let me take a look at what that looks like.
Good.
yeah, that's how my, you can even just Google.
Oh, there they are.
Oh, sweet.
Matthew, statistical reasoning plus on YouTube. And
Oh, that
it'll pull
comes up?
all his classes.
That's kind of cool.
Yeah, it'll
Yeah,
pull
try
all
to
of-
get the sections and the dates on there so you can kind of zoom into where you need to be.
Yeah. Yeah, we're on the internet.
Yeah, it's kind of weird.
Yeah. I wonder how many like people are watching your videos and actually how because I was in high school.
I know.
That's a good question. I'm really bad at YouTube. I don't know.
How many subscribers you got?
Like 30 or something,
there's like-
nothing major.
I think there was at least that when I subscribed.
Yeah.
That's
I was
awesome.
like, I need to, at least for now, I'm subscribed to my college.
Well, another thought is if you make a comment on a video, I actually get an email about it. You could really just make a comment and say, hey, Mike, at this timestamp, I'm not too sure what you meant, and I'd be happy to clarify.
That's cool.
That's a weird way to participate in class, but it works.
Yeah.
It's like email.
Like on YouTube. if you-
On the actual YouTube, yeah. Yeah, I see those comments, so I would reply to them.